today, by the end of the lesson today, you'll able to know a couple things. Be able to describe the difference between electric force and electric field. Be able to discern which equations to use to calculate the electric field and determine the direction of electric force and the electric field. Did you guys notice as you walked in here, this space right here? Weird. It's weird. It's right there. Do you see it?
Oh yeah.
I don't either. But it's no, I'm serious. It's weird. Check this out. So this ball has mass, right? Has inertia. It wants to. What does it want to do if it's at rest? What does it want to do? Stay at rest. Check this out. It has been doing that all morning long. Like, what in the world? Check it. Look. At rest. It's at rest. It's obvious at rest. It obviously wants to stay there. And it's as if something goes, no, come down. Crazy. Okay, breaking character. Mr. Smiley, that's called gravity. Okay, now, at this location, is there a force of gravity? Yes. If I take away the ball and I take away any air molecules in this space, is there still a force of gravity in this location? No. Because the because the force of gravity requires two masses. Okay, we've got one mass, the Earth. Second mass right there, nothing. But what we do have is a gravitational field. In this location, there's a gravitational field. If we take something with mass and we place it in that gravitational field, then there's a gravitational force. There's a gravitational field all around the Earth. Everybody okay with that? Can you visualize? Like, you don't see it, but it's a thing. Like, you stick something with mass in the gravitational field, it'll experience a force. Okay, so a field in general. This is the potential of. I'm gonna stay away from potential because we're gonna use that word next week a lot for another context. So I'm gonna change that potential to the promise of. The promise of a force at a certain location. It's the promise of a force at a certain location. Okay? In this space, there's a gravitational field. Okay? There's the promise of a force. If I take something with mass and I stick it in that gravitational field, all of a sudden, like, boom, force, that promise is fulfilled. There is a force. Okay, and what that field can also tell me is how much that force is going to be. If I take something else with another mass and I stick it in there, that can tell me how much force this is going to experience. How are we doing with that idea? Kind of a weird idea. Okay, now that's with gravity. I introduce you to the Van de Graaff generator. Okay, now here's how this works. Down here is a spool made of material that is really okay losing electrons. The rubber band is okay taking the electrons. So as this spins, this acts like a conveyor belt for electrons, bringing it up here. There's a metal comb up here that acts like a combine and harvests the electrons off of the rubber band. That metal comb is connected to these copper leads here, which are touching this metal ball. So electrons are going on down the copper and onto here. Where do electrons go on a conductor, on a aluminum ball? Where do they go? Where they reside? Where they live? On the outside. On a conductor, the charge always resides or stays on the outer surface. Okay with that? Okay. Now, if I turn this on, there's something weird around that space. Do you see it? I don't either, but it's weird. Okay. Now, what I'm going to say is there's an electric field. Okay. Now, does everybody see the packaging peanut? Okay. Think about what's happening to the electrons. Okay. Negatively charged. Think what's going on inside the peanut. Take my finger. Tell your neighbor what the charge on the packaging peanut is. Okay, the charge is positive. If that still is elusive to you, chew on it a little bit. Okay, so this is our packaging peanut. Where we know that. We're going to call this our test charge. Okay, this is in the video I call it a test charge. We can call it a scout. Okay, this is going to scout out, survey the area. Okay, scout. Yes, sir. I want you to check out the area. On it, sir. Looks good, sir. Over here. Looks all right. Okay, we're good over here. All right, keep it going. Oh, sir, I'm getting some readings. Sir, this is weird over here. Sir, that's kind of weird. Oh, sir. Sir, that's so. How is it weird? I don't know. It's just really weird. It like took me in there. I don't know. Like I'll just. Okay, go. Be careful. Go keep checking out. I'm trying. Scout. Are you there? Scout. Oh, we lost another one. All right. All right. So around this charged object, is there an electric force? Or is there an electric field? There's an electric field around here. Okay? It is the promise of an electric force. Okay? So, this is the promise of an electric force at a certain location. Okay, it's the promise of an electric force at a certain location. Okay? Now, the promise is fulfilled meaning an electric force is experienced if a charged object is placed in the electric field. Okay. Promise is fulfilled and an electric force is experienced if a charged object is placed in the electric field. Okay. Now, when I was in your shoes, I was like, this is absolutely stupid. Like, why would you come up with a whole nother term for something you don't need? You could just use Coulomb's law. Okay. Like, why don't we just use this thing? Because sometimes, let's pretend I put a curtain over this and you couldn't see what's behind the curtain. I could take my test charge and scat out the area and record the force that the test charge experienced. We use the word field appropriately. Like, think about that. Like, we're mapping out this field, this area, this space. And we're saying how much force here, how much force here. And from that, we can figure out, we can communicate in this location. We know that there's a field. We don't know necessarily what's causing it. We have no idea what's behind this curtain. It could be 1,000 Van der Graaf generators. Could be like this weird shape. Whatever. I don't know. It doesn't matter. But what we do know is this area, the space in here, it's weird. So we don't necessarily need to know what causes it. That we just know this area. If you stick a charge in this location, you're going to experience a force. Okay, and it's so in that way, it's kind of an idea. But as we will study more this semester, it's more than an idea. Electric field is a thing that exists by itself. Like, so it is like a physical. I don't know if physical is the right word, but it's like an actual thing. Okay, so everybody okay with this? So we're kind of, we will see. Tell your neighbor. Correct answer is was the Van der Graaf generator charged? Yes. Was the space around here weird? Yes. What do we say is what we say is in this space? It's present in the space. There's a field. There's an electric field. Correct answer is B. Beautiful butterflies. Okay. There's an electric field. There's not a force. A force requires two charges, Q1 and Q2. This one, there's just one there's just a field present. If you stick another charge like the test charge in that field, it's going to experience a force. Okay, good with that? Don't be influenced. Stand fast. All right, so I put some numbers to our scenario here. Oh, I want to change these numbers. Oh, let's change these. Hold on, let's think of something here. Give me something good. Let's do 3. That works. We'll do this. Oh, I want to do that. Shoot. Oh, hold on a second. I should probably pause the video. That's probably why. Let's take that down a notch. Oh, shoot. I like that better. Oh, that's a long way away. All right, we're just going to go with it. Yeah. Whatever. Okay. Sorry. Just a little recess there. All right, we're going to stick with what we have. All right, so we've got those charges, distance, separation, and force. Now, what makes this electric field confusing is the fact that we have two equations that describe an electric field. Okay, we'll call that equation 1 and equation 2. So, from the point of view of the packing peanut, and this is tapping on the stuff that we had in the video. Which equation should I use from the perspective of the packaging peanut? What the scout experienced? Equation 1, equation 2. Give me a vote, and 0 if you got nothing. Just so I know you're like alive and following along. Okay. Correct answer is 1. Okay. This is the charge on object experiencing the electric field. This is the charge on the object experiencing or in the electric field. So given 13.76 newtons and you have 3 times 10 to the negative 6 coulombs. And when I do that, I get 4.59 times 10 to the 6th. Okay, now with this chapter in particular, when we're doing last semester, we could look at stuff and say, does this make sense? Like, look at our calculator, like, is this real life? This is like no idea. We have zero context. Let me try to give you some context. Electric fields are going to be big numbers. You're going to be in the thousands or the millions. They're big. Okay. And what's the unit on that? Newtons per coulomb. Okay, newtons per coulomb is the unit for electric field. Okay. So, from the perspective of the Van der Graaf generator, the object that's creating the electric field, which equation do you think I should use? Well, if you used one already, probably 2. Okay, yes, but let me tell you, so this is the charge on object creating the electric field. This one's creating, this one's experiencing. Okay. Think about it just from a very conceptual point of view. Without looking at the equation, just tell me, what do you think happens to the strength of the electric field as you go away from the Van der Graaf generator? Do you think it gets weaker or stronger? As you go away from the Van der Graaf generator, as you go away from the source, the strength of the electric field is going to get weaker. As the D gets bigger, what happens to the electric field? Decreases. Does that make sense? This describes, hey, as you get away from the source, the electric field is going to get weaker. Okay? This is K Q2 over D squared. So you have 8.99 times 10 to the 9th times 250 times 10 to the negative 6. We're dropping the positive and negative charge, so I'm not worried about it's negative 250. I don't care about that. I'm dropping that negative sign there, and divided by 0.7 meters. Remember to square that. I have a hypothesis of that electric field. What that value is going to be. Anybody else have a hypothesis of what that value is going to be? Okay. It is 4.59 times 10 to the 6th. It's the same electric field. It's just from 2 different points of view. One from the object creating the electric field. The other one's from the object in the electric field experiencing it, like, whoa, from the scout's point of view. Okay. So in this problem, I gave you everything on the worksheet over the weekend. You're going to have to discern what I've given you and what equation you're going to use, because if you don't pick the right thing, it's not going to work out well. Okay? This is the thing in or experiencing the electric field. This is the thing creating it, the source. Okay? So if we have the charge of an object, then we're going to use the first equation. But if we don't have that, you just have to. No, you have to, so here's what I could give you. I could say, here's the charge on the peanut, and here's the charge on the Van der Graaf generator, and it experienced a force, the peanut experienced a force of that much. So which equation are you going to use? So like I left off this. So you're like, shoot, I have to use one of these. Which one I'm going to pick? I'm going to be picking the one that's experiencing that. Therefore, I'm going to use one. Okay? Good with that? All right. This question is kind of lame. What this is getting at is, this is like the 1 over x squared thing. As this gets bigger, this drops off really fast because it's squared. It's inverse square law. Good with that? All right, this is straight up from the quiz. Correct answer is A. Okay, now here's how you remember this. Positively charged objects create outward directed fields, like sunshine. Yay. Okay, it's outward. Negatively charged objects create inward directed. I just feel sorry for myself. Okay. They're just focused on themselves. Sunshine, negative. Good. Okay. So here's a couple things. Number one, there's nothing moving in the direction of the electric field. These arrows are just a way to communicate a distinction between electric fields created by positively charged objects and negatively charged objects. There's nothing moving in that direction. The arrows don't say motion. Okay? It's just a way to communicate. Okay? The second thing is someone just came up with this convention and we went with it. Okay, like why did positive out? Someone decided, one day, positives, let's make them outward directed fields. Negative, let's go. It's kind of like your parents gave you a name. They had some rationale at the time, but at the end of the day, when you introduce yourself, like we just say, okay, sounds good. We don't really question it. We just say, okay, that's what your parents gave you. That's what we're going to call you. Easy. Good with that? Okay. All right, I want to know the direction of the electric field at point X from that charge. Okay. Tell your neighbor. Is everybody okay with D? This is positive sunshine outward and at point X going in that direction. Good with that? Okay. Thumbs up when you have a guess. Have a conversation and tell your neighbor why.
I think it's A because I feel like it is B, but it's Can I see this right now? Well, how long is it gonna take me?
10 minutes.
I just don't wanna be late.
Okay, correct answer is? Okay, here we go. Ready? A negatively charged object is being repelled by an unknown charge. Therefore, what is the charge on this unknown charge? It's repelled, has to be the like charge, so it's negative charge. What field, which direction is a negatively charged object create? Inward directed field. A is the correct answer. Do not, ready? Do not assume the direction of the force is the same as the direction of the field. It's a 50-50 chance. Not something good to bank on. Okay? Direction of the force is not the same as electric field. Sometimes it is, sometimes it's not. Don't look at that. So this is the type of skill that you're going to have to do on the homework this weekend, kind of detective work, looking at the problem like, okay, what's this doing? Oh, this means that, and this means, that's how you're going to have to work it. Okay? All right, example problem. You have object A has a charge of positive 2 microcoulombs, is 10 centimeters away from object B, which also has a charge of positive 2 microcoulombs. What is the net electric field 4 centimeters away from object A, between object A and object B? Okay, so what I want you to do here are the equations in your toolbox so far. You got 2 electric field equations, and then you have Coulomb's law, which defines the force. I want to know the total of the net electric field at this location in between these 2 charged objects. Okay? So I want you to come up with a strategy. Don't break out your calculators. I just want you to strategize. What is it that I'm looking for? How am I going to find it? Just want a strategy. What equation we're going to use? All right. Thumbs up when you have a strategy. You don't need any, like, I don't need you to pick up any equation. I just want you to strategize. Thumbs up if you have a strategy. How are you going to approach this problem? What are you going to do? Okay. I'm looking for the electric field, the total electric field at this location. Do I have a charge at this location? No. What do I have here? A force or a field at this location? I have a field. Okay. I have something that's creating a field here. Sorry. Then creating a field is this and B. So what I'm going to use is equation 2. So that's the charge creating it a certain distance away. Okay. So the electric field from A, I'm using this equation. Oops. So I've got 8.99 times 10 to the 9th times 2 times 10 to the negative 6th coulombs per microcoulombs divided by 4 centimeters, 0.04 meters, squaring that. Find that to be it. I know this is improper scientific notation. It's just going to help me. So I find that to be 11.2 times 10 to the 6th. Newtons per coulomb. Okay. Now, B is also creating an electric field at point X. Okay. So I'm going to use that same equation for this location here. Now, my distance is at 10. This distance there. So 6 centimeters. So I got 2 times 10 to the negative 6 coulombs over 0.06 meters. Remember to square that. And I find the electric field at point X from B to be 5 times 10 to the 6th newtons per coulomb. So we got 2 electric fields. Lexi.
Can you just assume that if you're given distance, you use the second equation?
Great question. So the question was, if you're just given distance, can you assume you can use the secondary equation? That would be true, except you have a jerk teacher that might give you distance just to be that guy. Okay. So, reminder that electric field is a vector. It has direction. I need to find the total, the net electric field. Okay. So, which way is the electric field at point X pointing from A? To the right or to the left? Tell your neighbor. Which way is the electric field from A pointing at point X? It's positive. Sunshine goes outward. At point X, that's going to the right. So you have 11.2 times 10 to the 6th. Tell your neighbor which way the electric field from object B is pointing at point X. It also is positive, so outward directed field. So at point X, it's going to the left at 5. So to find the net electric field, what am I going to do mathematically? Because you're going in opposite directions, I'm going to subtract. So I get that to be 6.2 times 10 to the 6th newtons per coulomb to the, tell me, right or left? Right, because the blue is bigger. Okay? So on the worksheet this weekend, you know how to do everything except for electric field lines. Okay, so when you see draw the electric field lines, just ignore that. We'll pick that up on Monday. Sound good? We got a test on Friday.